everyone, and thank you for coming to my presentation. I want to thank Dr. Fang and the organizing committee for their invitation to present this talk. I'll be talking about computational modeling of particle transport and deposition with some environmental and biological application. As the outline of the talk, we'll talk a little bit about general properties of aerosol transport. We'll be focusing on computational modeling. We will show some indoor applications, some respiratory, some probably application to transmission of COVID-19. And due to talking and possibly coughing, and we'll show some sample studies for a small office room and a larger office room and conclude. Well, basically for the modeling airflow, as I'm sure this community is well aware, there are different techniques. DNS, direct numerical simulation, is probably most accurate, but very expensive and also not practical for complex geometries. Large eddy simulation has come along quite a bit. Now it can be applied, still is extensive calculation, but becoming more practical as the computer power increases. A RANS model with various turbulence model are still, it seems to be the practical approach to solve, simulate airflow and aerosol transport. And at one point that if you want to do the aerosol transport is that the particles are very small and they are subjected to the fluctuation of turbulence. And if you're using RAND that averages the Navier-Stokes equation, we need to generate somehow the fluctuation and to account properly for the dispersion of the particulate matter. If you're using direct numerical simulation, of course, you don't have to worry about this because it's already resolved all the scales of turbulence. If you're doing large eddy simulation, you still need to do simulate the fluctuation of the large subgrid scale. If you're using RANs that become, there are different models like Gaussian model, we refer to as continuous random walk or discrete random walk. Some of them are in commercial codes, and also PDF model is other models for this application. I'll show you only one equation. That's the equation of a motion of a small particle subject to the drag force, possibly lift force, gravity, if they're submicron, Brownian motion, and if they're charged electrical forces. Typically, in many of the applications, the aerosol concentration are dilute and one-way coupling is sufficient. And that's what I assume in most of the work I'm going to show today. If the concentration is not dilute, then aerosol interaction or particle interaction and collision, etc., become important that need to be accounted for. We are using here nonlinear drag effect, and that's the model shown in here. And I just want to point out, it's a commercial use of one of the older paper here that's basically we did a simple channel flow and tested the accuracy of various, schemes. This is deposition velocity, which is the flux to the wall per unit concentration, per unit area, and versus relaxation particle of the particle relaxation time. And the experimental data for aerosol transport is this kind of small little circles here, which have a U-shaped variation basically in this graph. And the various simulations are shown here, and these are the one on the top here are conventional CRW and DRW model when it's used here and without near wall correction, which seems to overestimate the deposition in certain size range by the order of more than 1,000 to 10,000 times. But in larger particle, there seems to be, probably okay on the whole. But to get this, and these are various empirical fit to the data and so on. And the one that I'm going to focus on is if we use the normalized kind of, CRW model, which is these graphs here, which is, shows a very reasonable answer. And there are some DNS of Marcholi here, which is also shown, which seems to be comparable to the normalized CRW model. And the other correction needed, and that's why I talk it over here, is very near the wall, V prime perpendicular to the wall direction is proportional to y squared. This is known from a statistical theory of turbulence, Henz's book, for example. And they, very close to the wall, therefore V plus goes with a square. And that's an important parameter to account for. We have done some DNS some years back and estimated this value for A here is about 0.008. And, and so this, many of the commercial code essentially assume linear interpolation and miss this. This is one source of the error. And of course, the normalized CRW normalization is also important to get the accurate answer. And there are a couple of recent papers on this. Then we can apply the one after some of the correction, we can apply the code to various applications. This is just a mannequin sitting in a room and some dust comes in and spreads. And the question is how they deposit, maybe how much is the exposure of the sitting mannequin for different kind of ventilation system. This is a kind of a hospital room. There are two patients here, and one maybe has some infectious disease, and he talks or coughs here, and some of the droplets that emitted moves around the room. And the question is, what are the probability of the other person getting infected? This is a mixing ventilation. We have tried it with displacement ventilation and so on. And the goal is to optimize this in some way that we could basically okay, this is an aircraft and in flight, and oops, that one person is coughing or talking and then spreads droplets, and depending on the air conditioning, the probability of exposure varies in different parts of the craft. We also did some application to, in respiratory deposition, with an NIOSH project some years back through the nose and lung, and just put a couple of summaries. We use this multi-level. Lung has 23 bifurcation, which is very hard to do all of it. I mean, people have gone up to about 10 bifurcation or so. But this is a multi-level lung that we did, piece by piece, essentially, and then we transport all the properties from the flow to, concentration of particle, etc., from one level to the next level, and that could be used to go to higher number of generation. As a sample, flow simulation, a real small movie clips is a 1 micron particle to trachea and left and last bronchus, and we can see that the deposition is kind of uniform, and most of it actually passed through this bifurcation. If you go to a much larger size, which is we use 30 to more dramatically show the effect, most of it deposit on the by impaction in this region, basically in the Kernighan region. We have also looked at different shape particles in some of the earlier works, and this is a small fiber which has a length of 1.2, an aspect ratio of 12, diameter of 0.1, and shows how it, essentially it stays parallel to the, to the wall most of the time. If you go to much smaller size here, the aspect ratio about 4, there's lots of oscillation. Of course, this is just for illustration. And the size are increased so we can see. There's another paper by my colleague, Dr. Omid Abu Ali, who will talk about some more recent result on the fiber transport in this session. This is another simulation with the Abu Ali's group, which is basically contains the nose as well as a part of the upper respiratory tract for sample trajectories. These are 20 micron particle and breathing rate of 7.5. More recently, Dr. Tian and myself looked at the similar kind of a study with nose breathing and mouth breathing, and looked at up to about 10 generation, including the upper respiratory system. Another interesting study was done by Abu Ali in 2015, his group, that's basically aspiration efficiency of when concentration. That has probably of interest to the COVID transmission, because we can concentrate droplet concentration in the room, and if somebody is there, the question is, what is the aspiration that person will see. And here, the green line is actually in the absence of thermal plume. That shows very small particle. Of course, we see 100%, aspiration. As you go to the larger star, it drops basically. With a positive thermal plume body being, warmer than the surrounding, the blue line actually forms, and this shows that the aspiration up to about probably I don't know, 15 micron, so it is very close to 100% or 95%. Then it drops, of course. And if the body is at a downward thermal flume, if the air around is hotter than the body, then it becomes much less. But the blue case is probably the more practical situation. I want to say a few words about some of the COVID study. It's known that, the direct transmission by touching was the main cause, was at least, believed at the beginning, but now we know aerosol transmission is even more serious by coughing, sneezing, and speech. And that basically is, the way it's most likely the COVID is transmitted. Coughing was studied by Duct long ago, and this is the distribution of the particles that at different sizes and number of droplets coming by coughing. There's actually a much larger size here, but we kept it up to less than 100 micron, which is the maximum size number of the particles. Yang and Feng also discussed the volumetric flow rate due to a typical cough, which is at 0.1 second is maximum and then decays, and these are in liter per minute. There's a recent study by Ahmadi, Wexler, and co-worker for speaking, and that shows for for kind of medium speaking, this kind of variation. The peak is about 1, and for loud speaking, the amplitude increases, but the diameter is basically has the similar form, and soft speaking is less basically like that. There's also studies on sneezing and so on, which I'll skip. Also, to look at the effect of mask, this is a study by Zhang et al. And Feng et al. For filtration efficiency of different kind of masks. We'll see most of the masks are effective for larger, droplet or particles more than 10 micron. But for smaller size, K95 is probably most effective. At the minimum is at about 0.1 is the worst efficiency, which is 95%. But then surgical mask is less, and cloth mask is much less in this region. So these are kind of the protection that the mask, which is completely has no leakage, essentially provides. We have used this data and a simplified model for coughing in a recent study by Balachander and co-worker. Without mask, actually, if someone coughs, this is the distribution of the particle that's emitted near a person. And this, of course, deposit, evaporates, and change size gradually in time. And then if, after about 1.5 seconds, basically the concentration that the person is exposed to is something like that. This is of the order of, 150 or so maximum here in this scaling, and the particle are less than 10 micron approximately. These are very logarithmic scale. If a person wears a mask and you can essentially filter it, basically the particle, we see that it drops significantly. It's become less than probably 2 micron size, and the peak is of the order of probably 50 or 60 in this 10 to the -6 in this scale. So it's quite a bit of protection, certainly. Showing you one, a new study which is still in process. Is 2-person room, 2-person office room, 2 mannequin are sitting, and one of them is speaking. And these are the dimension of the room and so on. And this mannequin on the right is speaking, and this shows the flow rate. The air conditioning system are shown in here. It's a mixing system. This is the outlet on this side. And it's basically, the maximum is being cut quite a bit, so we can see the level of, enlarge the level of that we can observe basically. And this is for air exchange rate of about 2.4. And if you have one for, speaking, 1 micron particle is the average size sort of what's used here. And we look at the concentration of the particle in the room, and we can see that the other person, get exposed, and we use different partition here to study the effect of partition and those factors. If you go to larger size, the gravity takes over quite a bit. For 100 micron, essentially all of the particle drop, and and the other person is safe. And for the partition, for larger particle helps a lot, but for a smaller one is not really makes a big difference. This compares, we have done a bunch of air change rates in this study from about 2 to about 5 here, and also considered for different partition size and so on. This is the sort of concentration near the receptor mannequin, and these are average concentration evaluated by CFD in the room, and these are the prediction of the fully mixed model basically. And we can see that fully mixed is comparable, but does not really, there's a account for the variation in the room, basically. So for accurate system, probably we need to use a CFD. This is a larger 9-office room at EPA, actually was modeled here. They're partitioned between people, and it's a very large room, is about 9 meter by 9 meter, kind of the area. And here we, each of these mannequin are speaking, and then we look at the flow field as well as concentration. This is number 4 is speaking here, and it's continuous speaking basically to get the kind of the worst scenario. And then this is the flow field here, mostly generated by air conditioning system, of course, in this room, and this is air change rate of about 3. And then we looked at particle size, distribution, assuming this person emits 1 micron particle, and the concentration here at the mouth of the person emitter is 1. So these are fraction of the concentration that's seen in the room. In this case, actually, in this area, air conditioning is kind of low, and most of the particles stay. In this case, the right side of the room is less exposed. And this one is, again, velocity magnitude for air change rate of 4 here, basically, for this person here, number 4, still speaking. And the trend is very similar to the lower rate. And these are the average concentration in the room. And obviously, in this case here, CFD predicts larger level of exposure in this area, basically. We have also done it for, number 5, which is in the middle, is essentially speaking, actually speaking toward the front, but the air circulation actually makes the flow to go backward. So the person sitting in the back side of the is exposed to the maximum, gets the maximum exposure. And these are the fully mixed estimate here, shown here for this. And again, fully mixed give you overall average, but the exposure varies significantly in the room. Here is a bar chart showing this is the emitter in the middle. Again, we cut this to 10 to the minus 3. Otherwise, if this really should be 1 here, then we don't see anything. But so this is 10 to the minus 3 scale. And we can see that when this person, speaks, and these are different, partition size and et cetera, and average and maximum concentrations. But anyway, the person in the back actually sees more, as we saw, because of the air conditioning. As you go further away, that some areas see much less, and some areas see the average. And this one for the same thing for 10 macron study, and 10 macron, of course, is also a gravitational effect become important and changes the variation. And I guess this graph, if you look at, we can see that, because of gravity, only the backside person sees quite a bit, but the other mannequins see very little exposure. We have done another study which is very detailed of speaking, and it's is an NSF project. This is the tooth here, and this is the lower lips, and this is the upper lips, and the person is saying F basically. And these are this kind of simulation condition here, and we have done it's a little movie here that shows how the flow goes basically. And the flow is extremely unsteady, actually, and flips up and down here in this region. And this kind of, totally steady state one may not be sufficient. This is something we are looking at and see how this will affect it. This is a study for a coughing person. This is a 1 micron droplet. This person coughs, and we show how it essentially, emitted and disperses in the room. And I can go to this one. Oops, sorry. This is the coughing 20 micron particle here. This is kind of average coughing. Again, we see that it comes, concentration builds, and then it decays in time, certainly. This is a study of transmission in a room. 2 mannequins are sitting across from each other. This is by Masumi Salmanzadeh and myself. It's a basically, we tested different kind of air conditioning system for exposure from mixing and ventilation, and this was for a speaking case. And we used the distribution of size, in this study. This one is mixing, and this one is actually displacement thickness base, displacement ventilation system. Another study by Abu Ali's group here is in a transmission in a train. Mannequins are seated in the train and one person is coughing, and we want to see what happens to the other person. The flow was simulated, and we also calculated the variation here. And it's straight coughing has a lot of exposure. If person coughs downward, the exposure will be less. And finally, this a teacher in the class is speaking and emitting coughing again, and this shows the distribution of particles in the room and at different time. And you see after about 50 seconds or larger, essentially dissipates. And and these are coughing velocity of 10 meters per second here in this case, and this is by Dr. Laxian and the group study. Finally, I want to summarize that aerosol transmission is the main mechanism for spread of COVID. The concentration of droplet decreases with distance from the source and with the increase of air change rate per hour. Computational modeling could provide an insight into developing mitigation measure, and masks are effective, so masks should be wear in public. I want to thank a lot of my colleagues for different kind of studies that we have done on aerosol and particle transport, and some more directly in this talk that I mentioned their name. Thank you very much. Can stop this.